So everybody open this model. ETABS, right? I don't know. Is it default? Let me see. Which is default setting? What is? Oh, okay. Okay. Looks like it, right? Oh, okay. Right. Similar or some sort of different, but it's pretty much similar, right? Than with the other software. But the structural engineering software. Okay. Again, Revit is not structural engineering software. Period. Production tool. So don't even mention that Revit. We're using Revit for analysis design. No. 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 Please. You need to, right? Revit is not structural software. It's a projection software, projection drawing, right? But we're using 3D geometry, so we're using Revit. Clearly, because I don't want you to deliver wrong message so that your potential employer has some wrong perception, right? This is final element software, relatively simple version. We're not talking about solid real 3D elements, but I think what you see is mostly line element and area elements, right? You see what you see? It's line. It's line, it's segment line and area, right? So we'll get into that. So today, just this is ETABS platform. It's an icon, shortcut icon, right? Nothing different. Then also either shortcut. Those are all every this command or shortcut is the main menu, but this is shortcut. So icon is something we commonly use. Some commands, yeah, they create this shortcut, right? This is something they recently added. Some model they showed all the hierarchy or something information on this property or window, the view. So you maybe click it, you can just see something in general, the item, but this is something maybe I don't usually use much. This is pretty new. I don't care. I don't usually use much. But some of them may be worth it to know. But first, what we care is this, right? This is something showing some information in general, current model, what is assigned, all the information. You could see it. But here, visually, what we try to understand is this. Move this. Okay. First thing, in order to create a model, what you need to define first? Units, right? Units, right? So in default, here is a unit, right? You're fully aware of it. When maybe I'll open it, new model. Let's say if I click the file new, I think it pop up some model initiation. This is something interesting. You may have to choose default or using different setting, but obviously you see that. Depends on if it's a metric project or US imperial project, you may have to choose the unit, right? Metrics or imperial, you need to choose it. You need to use the right unit for your project. So here, user-based default, but you may have to, we'll get into that when we have ETABS 101 session, but we're gonna just go back to open this. So we're gonna briefly talk about it and then we're gonna start running analysis. So this model and everything is ready, right? I draw the line wall, but they are all representing same shear wall, concrete wall. But I show you line elements here, area element here. Those are identical, should be identical, but it's numerically I chose line here, right, and area here. But I just same thing when I just measured, right? So this has a more force mesh, right? So what you see is geometry. Overall, the wall. Obviously, the floor to floor height. How do you know it? Go to edit, and then here, edit story and grid system. You should be able to see it. This is story data, right? Story data. Because ETABS is more building oriented, so story data is the first thing I usually define. After I choose a unit, I usually define the story data, floor to floor height. So 10, total 10 open. So I make 100 feet tall. Yeah. Story data here. So this is something, go to edit. And here, edit story and grid system. Okay. When you go there, here's the story data, modify story data. All right. So this is once you choose the blend, open the blend model and choose obviously with the unit. And first thing, what I usually do is define the floor. So this is because they already set it up. I have a total this floor information, but if you open the blend one, it may have only one story. You need to add copy and define number of floor you needed, right? And then you type this each floor to floor height. Right? We're gonna get into that, but this at least how this is how to define the building height. And then you see the boundary condition at the bottom. I'm gonna zoom in. So rectangular is mean the fixed condition. You know what is a fixed condition, right? And then triangular shape is a pin. So okay, this is 2D. What I'm showing you is XZ plane, but let me show you 3D. So you see that this in the 3D space, right? This in the 3D space, and but the obvious line and wall area element. So it has a boundary condition. So this is 3D view. What you see. And for the checking the loading here, go to display, load assignment, right? Because our problem homework 1 has a joint load. I think I assign 100 kips in the win load. Let's see. See? I'm gonna increase the hold on font size, text option, graphic. Here I'm gonna make this is 7. So fonts I'm gonna make it bigger. Okay, 100 kips there. I assign as a point load. Do you see that? 100 kips, right? So this is our same the point loading for homework 1. Since we are in, we don't have to show the 3D. I'm gonna put this one on back to the elevation. What you can see, there are the 3D icon, right? 3D space view. If you wanna look at the plan view, click the plan view, but you see that you should be able to choose a story floors, right? Obviously, if you choose this, you see that representing the cross section, right? Of the wall. It's a 10 feet, 10 feet, 10 feet. But this area element, so we already drew as a wall area element. But since we're using line element, this section property should have that our 1 foot by 10 feet the cross section. But on the plan, you see that it show that their cross section profile, right? I'm gonna put it in 3D and also an elevation. So let's say I don't know what is that grid point one. Let me just click it and choose randomly A. Let me see. Okay, it's not on grid A. So here also this arrow bottom here, right? You can. I'm gonna click it and find out that our oh no, this is loading. Sorry, I'm gonna unlock. Click this on the phone configuration and I'm gonna click the elevation. I think this one's oh no, oh this one, oh yeah, oh this one. So on the elevation, when you click it, right? If I click it, it show the elevation view A, but you could just move around by clicking this, so you can move around that elevation view, so you can find out the elevation view, or you already know it on the plan view. So this I don't actually designate some bubble, so I don't know. Oh, here one, right? Here's a grid 1. So there's another one. Okay, so maybe we have a 2-1. So plan view elevation. Oh, there is a 1 here, another 1 here. Let me choose this one. Oh, might be this one. So I may have to maybe rename it. Okay, so this bottom elevation 1 is the elevation B1 is showing all the building profile. So we know that point loading and section property. Oh, So one thing that I didn't mention is section properties. This line element, right, representing a wall. Right click, you could see that all the properties. It's pretty much similar. If you click and right click, you open all the property information here. Section property, I define 12 by 120 C4, right? This is section property, cross section information. So define section and frame section. So 12 by 126. So W12 by 120 C4 is the one section property I'm using it. So when you open it, you see that this wall width is 12 inches, depth is 120 inches, concrete strength 4,000 psi. So this is something that usually manually you define the properties, right? The steel, we usually have W roll section database, so we're using AISC steel property data, but concrete, we don't have it. So usually this is typically they define the property. So this is frame properties. I define it, assign to along this line. Also, now this area, when you right click, you'll see the same information, but assignment here, it has a section property W12C4. The difference is because this area element, you already draw the wall as long as 10 feet. So what you need to define is thickness of the wall. Get it? Right? You need to define the cross section. For line elements, you don't have any cross section, geometrically cross sectional information of this line. So you need to define sectional property, which has a width is 12 inches, depth is 120 inches. So we're using section property, frame section property, and assign to this line. But this area, well, I already drew it as kind of with lengths, 10 feet, right? So this area element only need thickness information. So when you right click, you see the W12 by C4 in section properties. And I'm gonna go to define section property. Here is a wall section. So those are all section property information. Here's define section property. You see the frame section. Frame section means line elements, beam, column type of sections. Property we actually define in here. But here slab, deck, wall, especially this is a wall element, wall. So we're using wall section here. And I'll show you some section property. Here I set it up W12 by C4. When I open it, right? See, I associate with the concrete strength 4,000, thickness with 12, right? The model times shell thing, something that I was just leave it for later. But you need to define all these properties. So let's recap a little bit. There's a difference between our hand calculation and finite element software. But most of them, we need to know all this input, right? Right? Modes, geometry, boundary condition, you should know it. And Young modulus, right? Moment of inertia, you should know it. So deflection calculation, you should always have all information for hand calculation and FM analysis calculation. You need to clearly define that. They should be able to, because deflection applying some beam theory, elasticity, the mechanics, so that they should calculate the deflection, right, by using the formula. But interestingly, right, in order to calculate the reaction and shear force diagram, moment diagram, you don't need any of these section properties. All you need is loading, boundary condition, and dimension. Right? This is simple, right? We have 100 tips here. What is reaction here? Should be 100 kips, right? External force, internal force, action, reaction. 100 kips horizontal loading pushing this way, we should get the 100 kips the other way because we only have a boundary condition at the bottom, right? But do we need to analyze it? We'll see. Now, how about the shear force diagram along this wall? What is the shear force should be look like? Constant shear force, 100 kips all the way down, right? We're gonna get into that. You don't need to analyze it. You only need to know it. You should be able to know 100 kips applied all the way through this entire length. We're gonna double check with this model. Bending moment diagram. Simple. This is cantilever. P times height, length. P times height, right? That's the bending moment at the base, right? I'm just give you the heads up. This is something is what is I'm using small model because what you learn or formula should be fully reflected on this 3D model, right? But slightly different way depends on how you model. So the first one is basically your hand calculation. We don't need any hand calculation FM analysis. So it's here on. If I think you could click this triangle. This is analysis button, or you could go to analyze and click the analysis button. But I click the triangular. So when you run it, I think since we have a couple of load cases, default is always that load cases. It show displacements, but this is not our interest, right? So only default because I'm gonna show you define and load pattern. I do have a dead load case, live load case, wind load case, but wind load case is our point load, lateral load. So this displacement I don't care. That's my interest. So I'm gonna I cannot move this. So first of all, here reactions. Let's check the reaction. So reaction button is here, right? This is icon. If I click this, oh, yeah, this cursor and capture screen doesn't work. Okay, here, right? Display support spring reaction. Click it. What I want to see the reaction due to the wind load. So wind load, I'm going to turn on component, reaction component. I click it and see. Okay, what do I have here? 100 kips, right? And here 50 and 50 because we have two support. Make sense? 50-50, right? Reaction. Obviously, it's common sense. We'll assume this goes uniform cross section. Each point's gonna share and reaches 100 kips at the base, so 50-50. But this is only one point, 100 kips. But summation should be matching 100 kips external forces, right? So this is reaction checking, right? And then if you are interested to look at the shear force, how you can check? So shear force and moment is more likely internal force, right? Our 100 kips external force, but internal forces apply that this wall section is experiencing inside internally. So this is we call member forces, right? External force 100 kips generating these internal forces. We happen to choose, call it axial force, either compression and tension, shear force, right? And then bending moment. Those are something our terminologies, but those are all internal forces. So here, display frame here, basically everything is in this here in display menu, right? So here I'm going to use shortcut. I'm going to choose same wind load, right? Right? So there are components I'm interested. Let's check the shear forces first. So what do you see? Shear force, constant shear, 100 kips, 100 kips, 100 kips. Because we have a pushing here, support boundary condition here. Everything is constant shear. Make sense? Right? Make sense? Sometimes I having a hard time to understand this too. What the heck shear? What is a shear force? It's kind of like a seizure or something. Two different components and opposite directions kind of is something the shear forces. Right? This is shear force diagram. This may be the simplest the understanding, and so you should know. But obviously, it's based upon cantilever, which is a beam, and we should get used to this. How about the moment? Then what kind of moment we have to turn on? Here is a local axis concept you need to understand. But let's choose a moment 3. All right, here's a bending moment diagram. 100 kips times 100 feet, 10,000 kipper. Make sense? Right? You get all same answer. I think I may have to explain one more stuff in order to get this all information. But this is a line frame element, right? So most likely all the output should come from this frame, included frame. This is wall area elements. I need to assign it here to collect this internal forces. So here, this one I'll show you, should collect the all member forces. Once we turn on check this peers, they show this member forces. So because I check frame and pier, it shows the bending moment diagram, right? From frame and piers. But do I need any material properties? No. We only need loading and dimension and boundary condition. So we should be able to calculate what's the maximum bending moment of the base, right? Now let's check the deflection. So what I'm showing is everything is same, even super tall building. I'm just going through checking this procedure, make sure every modeling I create is make sense or behave, and double checking based upon all my engineering judgments, understanding. You need to really do this starting from simple. Yes. Huh? Oh, okay. It's a local orientation. Now, good point. Because this is also 2D analysis, but it created in the 3D space, right? So look at the X, Y. This is global coordinate system. Global coordinate system, right? So most likely assigning loading here, reactions, boundary condition, we follow global coordinate system, X, Y, Z. X, Y, Z, global. But local member, look, each member doesn't have to be follow always global axis, global axis. Because if this column is extended, they are not matching, right? So we need to understand global coordinate system and your local member oriented local axis later on. But for now, this is 2D. But here, I'm gonna, okay, here, check box. Need to shrink. Okay. Here, checkbox. Then you're gonna use this one a lot. It's usually turn on and off. So yeah, this checkbox, because this is something always using turn on and off, turn on and off. Previous we always do it because there are too many stuff. So I try to turn off all of this. But here, what I'm trying to show you in the object assignment here, where it is frame analysis, local access, frame, local access, right? See that it's a local access. I'm gonna turn on the local access and show you what this local access looks like. Here. This is frame element, so I turn on the local access. So you see this? Right? Maybe show you in 3D, so you see the all X, Y, Z. So put it in 3D. So see that? So local access. So red is local access 1, right? This is local access 2, and 1, 2, 3. Yeah, maybe 1, 2, 3. So 1, 2, 3. So based upon this local access, it's because it's relevant with associated with your cross section properties. And here I'll show you how this guy representing in your frame section. That is this here. Here. You show this cross section line and 12 inches with 120 inches steps. It shows that this is local axis 3 here, local axis 2, right? So you show that, oh, this is local axis, which means our interest moment of inertia should be about 3. Get it? Our form of 1, our loading is in plane, B is going this direction, right? Our interest associated moment of inertia should be about local axis 3. So moment of motion when you calculate it should be about this local axis 3. So you should calculate uh, the width times length cube divided by 12, right? I in order to calculate the moment of inertia I. But that should be kind of consistent because this is something concept I always confuse. It's because the moment is something killing me. Shear is okay. When we talk about shear, when pushing shear here, right? Our wall, our point loading is going in this direction, parallel to the wall, right? So our reaction should be on this plane, opposite direction. We saw it, right? The shear forces I show you should be on the local axis too. Let's double check. So shear is more straightforward as parallel to their loading direction. But moment, this kind of ridiculous moment, I don't like this terminology. We always using above axis, right? Because the moment is we always using above. So associated movement, we know this moment should be above this direction because the wind is pushing this and generating movement about this local axis during because you know this is kind of the effect of moment when the moment is happening, but we always use moment. Use moment is associated with this some axis or above. So this is always confusing. So 2 and 3 is a local axis. I want you to remember. So V2 shear force. Okay, shear 2 is 2. It means shear force in 2 directions. Shear 3 is about 3, right? Moment about 2 is about this 2, right? Moment about 3 is about 3, right? So we need to follow local axis. Just a little bit of concept. Just let's think about it. Because the reason why I think our model is very simple, is on two-dimensional, XZ plane. So you already know briefly. But in space frame, every member is rotated. So you need to really clearly define the local axis properly. Otherwise, you kind of get the wrong the forces. So let me see. So I'm explain local axis, and this shell elements things is also there in the shell elements. I'm gonna turn on the local axis here too. So let me zoom in. So you see that local axis, this area element has some default one direction, two direction out of 20 degrees. So this is their own default local axis setting. When you draw the wall, you're gonna typically got this. Okay, let me get back. So again, with that, right? So let's double check again. I'm checking shear force 2. So you see all the shear forces 2 because this is local axis 2. So you see, if you click shear force 3, you're not going to get anything because there is no forces in the outer plane, right? Make sense, right? Is it a little bit numerical stuff? Obviously, in the model, we need to get used to it because we need to define the geometry orientation of a member because our structure will be, they are 3D elements. So we need to get used to this 3D geometrical coordination system. Globally, global coordinate, local coordinate. You're gonna use it everywhere. So think about it a little bit, get used to this, right? Because you need to something, no matter what you do, anything you build, everything is 3D. So you need to understand this kind of nomenclature. So now let's see our homework 1. So I'm click the deformation here, shape. You could go to display, choose deformation shape here. Shortcut is right here, right? So I'm gonna choose win, right? Then let's see apply, right? First of all, number is the second, the pure bending mode. We call this the bending flexural bonding. It's a pure cantilever, right? Because it's also aspect ratio is pretty long. Height divided by width something more bending governing. So looks like curvature. Okay, very similar, right? Now check the. You should be interested. How about number 9.3, 9.2, 9.2, 9.3, 9.3, 9.3. Can we add another decimal point? The show unit. So here, displacement. I'm gonna add drift. Let's see. 9.31, 9.18, 9.18, 9.27, 9.26, 9.26. See the difference? Is it a big problem or just acceptable range? Plus minus. We are engineer. We are doing using applied science, judgment, right? Your head calculation come up with a 9 point what? 3, 2, right? That's a theoretical number based upon our beam theory formula. Oh, we truncate something Young modulus, right? And also moment of inertia, you may be, oh, yeah, I think that's full. Somehow our formula theoretical number shows us 9.23. But here, finite element software using beam element first model estimation is 9.31, a little bit overestimate, right? 9.31 versus 9.23, what? 1% difference, 2% difference, 5% difference, right? How about 9.18? Oh, area elements somehow overestimate the stiffness relatively. You see the 9.18 versus 9.31. Our three theoretical number is 9.23. You see the difference? Line element somehow has a tendency to a little bit overestimate the deflection, right? This is finite element software. Internally, have you taken any stiffness metrics class? I think that's maybe graduate. But internally, right? Line element, this is something that you need to kind of acknowledge it because this is because we're using line element one support, everything is based on just one line. So internally they calculate stiffness, right? Internal stiffness matrix finite element. They estimate 9.31, slightly overestimate, right? Than our theoretical number. Here, area elements are. Wait a minute, instead of 1.6, the pin, but since we have two pin is work like a coupling forces, so this is representing fixed condition. So we have two legs. Even though one leg, since one leg we need to assign a fixed boundary condition, since we have two legs, work like a fixed condition. So you can see the general coupling forces. I will show you interesting stuff. But obviously this estimation is 9.18. A little bit overestimate the stiffness, right? I can say that stiffness they overestimate maybe because boundary condition or something numerical internal method. 9.18 versus 9.31. You see that difference? But does it matter? This is engineering judgment. Because how do you know then how can you make a judgment? With a lot of experience and parallel study based upon understanding theoretical number versus finite element. You need to build some sense, right? Same thing. Who's the drivers doing always tailgating? Is that tailgating? Right? I hate that. Every day, some guys always do that. I hate that. Right? They think they are driving fast or but you thing is a sense of distance, right? Basically something sense we need to develop engineering sense. When you drive fast, somehow you want to keep the distance. So you know that how fast and how soon you can step on your brake and adjust the those are kind of sense, right? Speed and distance sense to protect, avoid any conflict or crash. Same thing. This is number, right? We're talking about number, right? Which one is which? Can we say this one is accurate than this, or still they are in the same ballpark, plus and minus 3% or 5%, 10%? Is this still acceptable, right? There is no absolute kind of guide, but plus minus 10% is sometimes acceptable ranges. This is 3% later, right? So something different method, we're using different method, right? Right? It's something consistency and overall just kind of performance. If that within some ranges, variation is very narrow. Your tennis performance is doesn't usually fluctuate too much. I think that is something I think we need to understand what is acceptable range of the output and how can we confirm this is acceptable, right? If this is number is double, triple difference times different, then obviously you like most likely you made a mistake in input. But if you got something similar range of output, obviously, yes. The, this is the it's mostly fundamental, the characteristic internal there, uh, maybe internal finite element, something, the theory inside, they overestimate because the 2 point and area element, they overstate slightly than line element. Only one thing that you should why, maybe because they have support here, two support is maybe more kind of overestimate, like has a tendency to overestimate. Also, we have using coarse mesh, like big one plate, which means this one and versus this one is slightly different because this one I just divide by 2 by 2, right?
What if you did one solid piece? Because like when I did my model,
Yeah.
homework,
Yeah.
I just did one.
Really? ETABS?
Yeah.
So what did you get then?
It was very difficult.
Yeah. Show me. This is good. Show me.
I got 7 inches.
It shows one panel from here to here, not divided. Typical original previous cell on the ETABS, if you draw from here to here, in order to draw it, you draw it on elevation, right? You click. You are kind of lazy to draw individual one. But it's interesting. Worth it to discuss. We talk about aspect ratio too. Area elements, right? If you draw it one big panel, right? We have aspect ratio 10 feet to 100. Aspect ratio 10, right? Internally, they don't or kind of probably has some tendency to understand their internal formula. There's something what can I say? Some misreading because it doesn't capture that proper elastic behavior. Because which one is something more close to which occasion physically? Uh, so hold on to that. So if you divide by 2, right, segments by segment, but the thing is, one thing is it's aspect ratio and also boundary condition. So you got deformation shape. If you have it, maybe oh, sure. Okay, see the deformation shape. Look at that deformation shape. Is it curved or straight?
Straight.
Right? Show me. You see, it's tilting, not bending. Right? Doesn't capture bending theory, elastic theory. So they don't usually follow bending theory. Somehow internally, it's misreading. This is engineering judgment too. Your knowledge, understanding of finite elements software should add this. You aspect ratio matter. Interestingly, ETABS previous version, if you draw, in order to draw this big as a one piece, if you have a defined floors, automatically they cut it. But some years somehow they get rid of it. So I think I am aware of it. Sometimes they try to draw the wall like this, but they don't cut it as the floor. But you see that misreading, right? It's bending. This is bending moment causing bending of the wall. Well, elastic bending. But that is not bending. It's mostly tilting, right? So it's something you need to aware. This is something tested. Good point. Find out. Then ask yourself, what caused it? This is more finite element software fit for. We need to user has to understand, right? We cannot rely on that method. It's not right. So that's why we need to kind of test it and show you a couple of examples. Since this is also part of relatively coarse mesh, this wall is relatively huge, 10 by 10. Can I use one or can I just mesh it more refinedly like this? This is one example to quite try and mesh it. I said deflection is a little bit more. Because now what has inside, they using this four nodes to form the stiffness, to define the internal stiffness. But obviously, since they have four nodes, what about inside? There are a lot of could be happening, right? Concrete shrink, right? Elongated under the bending, right? But since this is big, coarse mesh has only a limited point, obviously it has tendency to overestimate the stiffness. Since I mesh it, I think that we allow certain internal displacement, strain, internal strain, right, happening. So we eventually end up a little more deflection, right? 9.27 versus 9.18. So 9.31. So might be this is close to this because this is with a mesh. If we define one, right, 2 by 3, 4 by 4, then this number might be getting closer to this, some degree. Something make sense? Right, this is finite element software. This is fundamentally before you, again, you're not just running tool. You need to understand the fundamental insight. This is finite element software. I think I want you to get used to this because structured software really been used what 30 years now, 40 years, right? Especially 2 years. Very SAP ETABS current version, I think it's now 24 5 years. So it's been advanced, but it's always fundamentally similar, right? So I want you to get used to this. Other software works similar, right? Different feature, but similar, very similar. So I want you to learn SAP and ETABS a little bit, and you maybe can easily catch up the other software too. But since this is world class, here is a one last one for this example. So homework one should be done quickly to do so. Here, now, vertical reactions. So here, let's see. To the window that I'm gonna show vertical reaction. Here, what do you see? You see? To the window, right? This doesn't show me the vertical component reaction. There's no vertical component, right? What you see is a moment at the base. This reaction, this boundary condition is a fix. You already learned what is a fix, right? The moment, the XYZ translation, and also you have a rotational resistance. So you're gonna have a moment here because you have only one point. You're not gonna have a vertical component. I think instead it's gonna be shown on the moment 100%. I'll show you the moment diagram. But since we have two component, right? See the coupling forces, right? We know that what is overturning moment, 10,000 kip foot, right? We have already calculated 100 kips at the top time, wall height 100 feet. So it's about 10,000 kip foot, right? At the base point moment. This area, because you have a 2 point, doesn't show the bending moment. Instead, they show us coupling forces. Do you see that? 1,000 times what? 10. This coupling forces show us 1,000, 10,000 bending moment effect, right? Depends on, but everything is same. We're talking about same, A plus B, B plus A. But since geometrically on the modeling, we're using line, we're using one node versus two nodes, they are same model visually. But internally, you need to understand how this loading is reflected on the point and moment should be now reflect into the component coupling forces. If you want to turn on the bending moment about Y, let's say. So this point in 3D, you'll see that bending moment 10,000. You see that? This column has a fixed boundary condition. So at the base, bending moment is 10,000 kPa here. There's a point, right? This is a very important kind of general in general. I want you to at least think about it. I videotape it. Maybe hopefully I can upload it. Hopefully voice is strong enough. But I want you to think twice, 3 times. Without this, I think going forward doesn't mean you're gonna get lost. But this is very, if you understand a few times, think about it, the next step is relatively easy, right? But exciting. If you want to put the dancing and put the animation, yeah, do so. This is all dancing, always celebrate to the win. This animation, this music is 25 years. Nothing, they should change this. Or we should be able to change this, right? No, you cannot. Can you? Where? I forgot. Where? Animation. Animation. Did they made it? Or volume turn off. But they don't. I don't think they have. Do I have it?
Options and animation.
Oh, animation sound. Okay, here. Okay. Oh, we should change that. All right. I mean, here, what do you see? Vision index. 25 years, nobody cared. They didn't change this animation sound. They only add this switch, turn off. Who cares? I can turn off the bottom here. Why they made it, right? Yeah, I would just add something engineers prepare the music on. But software industry, this software has been well advanced. What I don't know what they develop. Most likely minor development, asking $10,000 per year. I mean, this is how software industry make business, right? One product they continuously upgrade it a little bit by a little bit, raise their price, and right, since they have a branding, people always use it. But what about us? Think about it. Our business model too. What we do, same thing. This is the biggest challenge you guys actually experience right away. But a little bit, let's think about it. So how we can do better. I'll also get paid.
What is the difference between this? What is the difference between this one that is non-commercial, not the commercial one?
How much? Same. This software, same. Because they gave us a discount. It's same, 100% same tool, but since they try to promote, right? This is business strategies. If you build some new product, you need to tackle younger generation, not old generation. Old generation is not gonna learn new. So they give us the discount to the college. Once you used to this, obviously you are the best one of VIP user for the future entire career, right? Also, they could advertise, oh, we are care about next generation. We will donate or discount to the college to learn our software. So we got discount, but they always protect not for commercial use. Obviously, I'm using it, but but obviously we have a company has it. I internally use it to kind of develop some material here, right? But my most likely, yeah. But this is the same. Rhino, when you download evaluation, is same thing, but obviously it has a limitation 90 days, right? If you really later on happen to purchase it, student version is $200, right? But commercial version is $1,000. So student same thing. They give us discount, but market is different. Come on. Rhino is worldwide. All designer use it. This small market, only few engineer. So think about it. This market is much big difference. Rhino and this, forget it. It's no competition. Rhino is much bigger, right? So without that, we could just submit your whole homework when I show everything. Just spend some time, exercise, right? Get used to this. Important. The homework tools, obviously I send it out, the same thing, but it's simply beam. We're gonna do the same exercise together, right? No, I haven't. Just so next week again. Oh, few. I have some issues. My son is also playing 12th grade football. So October 10th, I have to be there. Parents, so October 10th, I'm not gonna hear the football game. I think the football game is usually Friday, but today I think today some but I think that October 10th specifically, student and parents should be there somehow. So probably if you guys willing to have the class Saturday, possible? What do you do? Huh? No? Impossible Saturday? Then June. So I can move over. June class. What is the power potential? Because that is a worst recording. Okay, let me see that what yeah the title the October 10th. But I think I can record it something where you can follow along, right? Yeah, let me figure out. So any progress? You know, did I lose you?